So, hi everyone. So, today our second lecture will be by Professor Shadab, and he's from TIFR. He mainly works on these galaxy surveys and other things. So, please, Shadab.
Thank you. Thanks a lot, Sudipta, and thanks to the organizer for inviting me to give this series of lecture. And thanks to ICTS for hosting us in this beautiful campus. So I'm going to talk about, in this lecture series, the title is given by the organizer, is Galaxy Survey. And so it's something which is not very clear what you would like to hear about Galaxy Survey, because it covers a large variety of things. And also, this is the first time I'm giving this kind of lecture series, so it will be experimental, and I would like it to be interactive as much as possible. If you have feedback, it will be very useful, and we can modify the lectures as we go along, right? So I'll be asking a lot of questions, and I hope that will be all right, and I hope you will be asking a lot of questions. So, you know, we are thinking about universe, and we are thinking about how to understand various aspects of things and do observations as well as do theoretical calculations and compare things and make sense of all of that. So what I would like to try to do, because it's not possible to cover all different details about the structure formation as well as large scale structure, how does that work, and going into the details of all aspects of galaxy survey and how do you go about and measure these things at the level of photon or electron. So I'd like to give some basic ideas, and I'd like you to sort of think about whatever you're working on, how that relate to galaxy survey, and how to think about how can you in principle use any aspect of galaxy survey if applicable. So among the student group here, all of you, how many of you are currently working on anything related to galaxy survey? Can I have a show of hand? No one? Okay, 1, 2, 3. Okay, 4. So I see. So it's 4 of you, only 4. So that's very interesting. And I think that might be because probably you have certain things in mind when you think about galaxy survey, and it's actually very diverse kind of topic. And I hope by the end of this lecture series, most of you will be working on certain aspect of galaxy survey using it. I'm sure all of you will be using it if you're working in any aspect of cosmology, something or other. So I've divided this. So actually, I have not planned all 5 lectures yet. I've only planned 3 lectures, more or less, and I will see what I want to do in the last 2 lectures. And so the first part of the lecture, I wanted to sort of just give a brief overview of the status of cosmology and status of galaxy survey, and motivate why it is even interesting. Why is it like right now so many people are talking about galaxy survey, and what are the kind of things going on? So let's start with really basic. So we are here under the umbrella of cosmology, and cosmology is certain kind of things, right? So we are really trying to understand essentially origin, evolution, and structure and future, and we want to sort of figure out what are the fundamental laws governing our universe as a whole to predict what are the kind of things we are interested in. And so what are the really big questions? And of course, this set of big questions will depend on who is talking, and everybody might not have same set of big questions. So I'll give you my perspective, and you can add if something is missing. Please feel free to raise hand and say, okay, this is also a big question which is missed in the slide. But before going to the big question, let's just come back and see what is our current view of universe, right? So what do we think? What is the current story? What is the lambda CDM picture looks like, so that we have a common language. When I say something, you should be able to relate to some part of this picture, right? So we sort of started with it. We are working in the lambda CDM picture where there's a Big Bang, and we just had a lecture about problems with the hot Big Bang and what are the issues we are trying to address. And there is a period where inflation happened, so everything was expanding very rapidly, and we like just Pablo discussed several aspects of this expansion and why we think this phase was there, how to think about it, and that kind of thing. And then beyond inflation, we sort of started thinking about, okay, what will be the kind of content of the universe? There will be photons and protons and baryons of different form, right? And they are in a big hot plasma, which cools down and then finally comes to a stage where we have CMB. So I'm sure all of you have seen this story before. And this is where is the beginning of observable universe so far. We might be able to reach beyond this if we see something beyond CMB, for example, cosmic neutrino background, which people are thinking about. But this is where our observable universe begins. And then beyond CMB, there is this patch where basically everything is dark, what we call dark ages. And there are experiments to probe these ages. If you have heard of experiments like various experiments trying to do this. And then beyond that, we go to the phase where we start seeing supermassive black holes, quasars, then we start seeing galaxies, and then we come today, right? So pretty much up from redshift of roughly 3 or 4, this whole region is covered by various different kind of galaxy surveys. So galaxy survey is not one thing, there are many kind of things. And anything you want to study will largely in electromagnetic spectrum will come under the umbrella of galaxy survey. Right? So anything in terms of the late time universe. So this is the major chunk we are dealing with. There are galaxy survey now, for example, if you consider JWST, which can probe much further, but in smaller patches of the sky, and then you can talk about this, like really this region a little bit more. Right. So given this picture, you can see the red points here is actually measurement from one particular survey called Sloan Digital Sky Survey. The green is again from Sloan Digital Sky Survey. These are what we call regular galaxies, and these red points are what we call quasars. So they have a supermassive black hole at the center of it, which is active and accreting, and so they are very bright, which is why we can see them so far away. Otherwise, we would not have been able to observe them with the kind of telescope used to observe them. All right. So now that we know that there is a story of the universe, and we are trying to break that story and see what part of that story is sort of not consistent with our true universe. But if you look at status of cosmology, this really sort of shows the kind of precision measurement we have access to now. So this is from CMB Planck mission. You can see the measurement of power spectrum of temperature fluctuation as a function of angular scale. And you can see the lambda CDM model fits really well to this scale, which is just sort of the measurement has grown over last 3 decades. So the lambda CDM model, which is sort of established in 1990, on the shoulder of looking at things like galaxy clustering, CMB, things like supernova, Baryon Acoustic Oscillation, really describes pretty much everything. But of course, there are issues, and we'll see those issues later on in this lecture as well as other lectures in this school, right? So there's already now there are this sort of this plot, and I don't know how many of you have seen this plot before and understand what this is. Anyone? Pablo, yeah, sure. But apart from Pablo, like experts, anyone in the student have seen this plot before? Or this is the first time you're seeing it? Or know what is plotted? What are the y-axis? What are the x-axis? What are you really looking at? Right. So no one? Naveen? Yeah. You have seen this plot? Do you know what is it really showing? Mm-hmm. Yeah. So what this is essentially what we call the power spectrum. So we are essentially talking about, let's say, if you want to think about in terms of, let's say, you're seeing an image of CMB in the sky, and you look at all this distortion. So this was there in one of my previous slide, right? So this kind of structure, right? So now you're looking at this image. How would you represent? Like, how do you represent and relate it to a model of the universe? This is the observation. Observation looks something like this. But how do you go about and represent this and sort of compare that with any sort of prediction in terms of a model? So that's the kind of thing you need to think about. And this is the kind of thing we'll be measuring in our tutorials later on. So the hope is that during the 5 tutorial, you should be able to measure the kind of quantity plotted there. And what is plotted there? What is plotted there is what is called pause spectrum. And in a very simple way, what we are trying to look at is there are these different spots of different temperatures, so red and blue, or hot and cold, whether there is any spatial correlation, which means if I look at a red spot here, what is the likelihood that I will find another red spot at certain angular distance from that, right? And then you do as a function of angle. Now you do that for all different spots. So you're trying to correlate the temperature as a function of position in the sky. So this is what we call 2-point correlation function. And the Fourier space of that, if you do this in a harmonic space, the same analysis, then that's what is called pause spectrum. So this is what is plotted in that plot. So what is plotted here is essentially the pause spectrum, which is looking at if you look at the angular distribution of CMB temperature projected into the harmonic space and ask the question, okay, as a function of L mode, which is Fourier conjugate of the angular distance in theta, what is the correlated power? What is the correlated temperature? All right. And this is the quantity, which is actually, I guess you're going to cover this, or maybe in the CMB. In the CMB lecture, you're going to look at how to actually calculate this from the theory. So let's say if you state there is an initial condition of the universe. The universe started in certain fashion in the hot Big Bang, and then there was a phase of inflation, and then depending on the idea of how things grows, what are the causal distances, you should be able to work out this pause spectrum, in fact. All right. So this is something you'll learn as a part of CMB lecture series. I think Rishi will cover that. But it's important to connect this. So we'll actually talk about same kind of quantity in the galaxy survey, right? So the idea is that with few parameters in lambda CDM model, you are able to predict this exact pause spectrum and match this very well. So this is what, and you look at each of these points comes with the error bar, right? So there are error bars plotted in each of these points, which almost disappears in these scales, and the line exactly goes through that. So that's the success of precision lambda CDM. So what are the big question given we have seen that if you look at surveys of various kind, things work very well. And so what are the sort of main question we're still trying to address? So some of the question which I think is worth highlighting in terms of the top line question is, what is the origin and fate of the universe? So we still don't know what is really the origin and the future, both because of various uncertainty in our understanding, and the model allows you all different possibility depending on what you think. For example, what is the cause of accelerated expansion of the universe can give you very different fate, and what is happening to the equation of state of dark energy. I'm throwing a lot of terms at you, which I hope many of these terms you have already heard and know a little bit about. If there are things which you have not heard at all, please ask question, and some of these things I'll come back to later on in more detail. So what is the universe made up of? So what is the content of the universe, right? So we have always heard in popular talks that there is roughly 70% of it is in the form of dark energy. How do you really model that? How do you predict that? Do you know how do we measure that, and how do you make that statement? This plot is actually how do you make that statement. If you change the amount of fraction of dark energy in the universe, actually not dark energy, since this is CMB, if you change the amount of dark matter in the universe, this plot is going to look different. If you change the amplitude of fluctuation in the initial universe, the primordial power spectrum, this is going to look different. So this is where what gives us those numbers. And so that's what you would like to model. And you know, a little bit more somewhat even far-fetched question is that if our universe is unique or there are multiple universes, so there are multiverse, which may not be possible to test as per the current surveys, but maybe something you want to keep thinking about and see if there will be any signature in galaxy survey or CMB survey or other kind of observations. The other side of it is that I've used the word galaxy so many times, right? But do we understand galaxies? How do they form and evolve? Because in galaxy survey, that's what you're going to look at and try to make sense of universe as a whole. So you need to have certain understanding of galaxy formation itself. And if you're interested in galaxy formation, then there are many interesting questions about the galaxies itself. How did galaxies form? What drives galaxy formation? How do supermassive black holes affect galaxy formation? What is the relationship between dark matter and galaxy formation? This kind of question is something you can ask if you're interested in galaxy formation. But even if you're not, if you're interested in cosmology, you need to have some level of understanding of this question, because if you want to use galaxies to make any statement about cosmology, you need to have some level of broader understanding of these things and being able to model that whatever you're observing, right? And this is, I've already talked about this. So the interconnection, okay? So how do cosmological processes influence galaxy formation? So can I change something in cosmology and galaxies will look very different? Can this happen? Or they are robust, they are independent of cosmology? How can we use galaxies to understand cosmology? So that's the part of the galaxy survey which you are doing. So if you have heard of JWST headline results, cosmology is broken because they found certain kind of galaxy. So that's where the connection comes in, right? And why would you use galaxies to understand cosmology? So this is really, I think, what I want to motivate. So anyone know or can think of why would you use galaxies to understand cosmology? Why do you want to do that? Okay, but why does that give an advantage? Mm-hmm. Right. Right. Yeah. So you gave the answer in the reverse way compared to what I expected. The thing is that in dark matter is something you cannot see directly. What can you see if you go in the night sky? With naked eye, you can only see stars in the Milky Way. But with a telescope, you can see galaxies. So the galaxies are the thing which you can see. You cannot see dark matter directly. And then you need to ask, is the galaxy connected to dark matter in some way, or cosmology in some way, or the structure as a whole in some way? And so that's the answer he just gave, that galaxies are what we call biased traces of dark matter. And again, what does this mean is something we'll come to. And this is actually part of the main paradigm of a structure formation. So since galaxies are the thing which we can see and observe, we would like to try to use that to understand cosmology, particularly nature of dark matter and dark energy, like probe both of those big questions, and then see how can you connect that. And so you need to then ask a question, how does galaxy connect to dark matter or whatever is there as a whole in terms of the large scale structure of the universe, if there's a large scale structure. Yes. So because it's stars, so how do we know that what part of galaxy formation is attributed to astrophysics and cosmology? How do we balance it? Right, so that's a great question, but maybe let's try to understand that question itself, right? You're saying that, okay, you see the stars in the sky, but you also see galaxies in the sky. Now, you see galaxies in the sky and you want to ask, okay, what part of what you're seeing is galaxy formation and what part of it has to do with cosmology. But then what do you see? When you see galaxies in the sky, what do you really see? Any guesses? Have you seen night sky? Anyone seen night sky in a dark place? Yeah, you have seen night sky. Yeah, so when you go and see with naked eye, you basically mostly see the Milky stars in the Milky Way, and so that's like really nearby universe. If you are at very good sight, you might be able to see Andromeda, which is our nearest galaxy, and you'll be able to see Messier objects, which I'll actually show in one of the later slides, a list of Messier objects, right? And so what you're seeing is the light coming from the galaxy, and the light coming from the galaxy is processed through galaxy formation physics as well as whatever is in between the galaxy and us. So all the intermediate objects, if they are dark matter and it's interacting with the light emitted from galaxy, it will interact. And in fact, that's a very key question. If you see a light coming from a source, what are all the possible interactions possible at the source, intermediate, and at the detector level? This is what is galaxy surveys about. So I will not answer how to address this question completely, but it's a good question to think about. And hopefully in later lecture, you'll see some facet of it. But it's $1 million question. We are sort of trying to understand that even now in terms of the frontier research. When you're trying to use galaxy survey to probe fundamental question, you're trying to ask that question and see what part of observation we can use, what we cannot, to make fundamental statements. Right. So those were sort of bigger level question, but then you need to ask a little bit more deeper, right? So you cannot work with that broader level question. Often you need to go and think a little bit more like, what can I ask with which we can I can sort of start doing something, right? And so there are sort of more detailed question. For example, what is the nature of dark energy? So now that if we accept that universe has something called dark energy, what is it? What is its nature? Does it evolve? Does it fluctuate? Is there perturbations in the dark energy? Does it cluster? Is it coupled to dark matter in any way? And so you can ask next level of, these are next level of question beyond the top level I told you, right? And then whatever is the nature, let's say you write down a model and you propose a nature, how can you probe that? Like, what are the kind of things you need to be able to observe and probe and differentiate between different models? So that's another thing you want to think about. And let's say you figure out a way to probe this. How are you going to optimize that so that you can claim, I can measure this at this precision, right? This is how you would want to go. If you want to design an experiment, you want to sort of convince people, because it's going to cost and effort and money and time from people. You need to have some estimate of, okay, how well you will do if you do this experiment in terms of whatever you want to probe. So how do you optimize experiment to get best constraint? And then you need to start asking question. Let's say once you have addressed that, is your method unbiased? So are you probing whatever you're probing is something to do with galaxy formation, or you're actually probing cosmology if you're making a cosmology statement? That's one example. But is your method unbiased generally? And once you go to measurement, errors becomes an important part. And so I hope I'll spend one lecture talking about just errors, and hopefully that will be an interesting lecture. So how do you sort of estimate realistic error when you claim a detection, when you say, okay, there's dark matter is doing something or dark energy is doing something? How do you think about errors in those quantities and say, okay, this is for sure doing something, or maybe doing something, that kind of statement, right? So 5 sigma, 10 sigma, these numbers if you have heard of. And finally, which I'll not talk about, but you need to think that how to gather money and support from people to actually get the experiment, get the computers and do the analysis to understand if your model of the universe is actually happening there or not, right? So I hope like you have now some basic common language to talk about, and all of you are convinced at some level, probably you already were, but I just wanted to do that again, that lambda CDM does describe our current observation very well, and there are some deviations, and we are not happy, right? So why are we not happy? We are not satisfied, because lambda CDM explains, but lambda and CDM both are the things which we don't understand. Like we are not satisfied with how we have put in lambda and CDM in the model. So we want to sort of break that and really figure out what is lambda and CDM. Okay, so we will sort of talk about this later on, but before continuing, I wanted to sort of give a brief history of galaxy surveys itself. So let's start with very early on in sort of, I'm sure humans were observing stars and galaxies even before that, but this is sort of where we have a sort of decent chunk of things which is related to galaxy survey. In 1780s, Charles Messier made a catalog of about 103 objects. Not all 103 is shown here. It's an image by NASA. I think this has only 100 of those objects. So this is our Milky Way, and these are the objects which Charles Messier in 1780s had made a catalog of. All right, and these were what they used to call nebulae, because from at that stage, when you were sort of looking at with a small telescope, they look like a fuzzy chunk of nebulae. And these are the locations of the objects in the sky. So in a modern catalog where the Milky Way is plotted there. And the debate was essentially at that time is what are these nebulae and what is the size of the universe. So at this stage, you have to forget all about dark energy, dark matter. You have to forget about the size of the universe. We are really thinking about, okay, is whatever we see in terms of in the sky is part of the universe? What is the size of it? Is it part of one big galaxy, or there are other galaxies beyond our galaxy, right? So what is really the size of the universe? Shapley and Curtis were two main names comes up if you look at that era. Now from there, we came to a bit more closer to the modern era, 1920 to 1960s. Mostly it comes in the name of Hubble, but I would like to highlight there are sort of three figures which were very important for this: Melvin Slipher, George Lemaitre, and Edwin Hubble. So what Melvin Slipher did is he had meticulously observed many objects spectroscopically. So he had measured in current world what we call redshift or recession velocities of large number of objects. That was a really hard task, and one by one he had done that measurement. George Lemaitre built up, essentially worked out the model of how expanding universe would look like at that time. And then what Hubble did is Hubble measured distances of these objects for which Slipher already had the recession velocity measured. So he measured precise distances of these objects and then plotted these together and came up with what is called Hubble law, and there is a proposal that we should call it Hubble-Lemaitre law, and this was shown in 1929. Right? So that's where it was a remarkable time because our view of universe changed quite significantly. Right? So now we're talking about that as you go further away from us, things are moving faster, so everything is expanding. At this time, as I want to keep mentioning, right? Even if you're interested in cosmology or galaxy formation, you always have to keep the other side in mind if you want to do frontier work. So at the same time, Hubble actually did the other side of the work as well, which is called Hubble tuning fork diagram, classifying how do these galaxies form and evolve to different shapes, right? So what he said is that galaxies start with elliptical nebulae and then goes through some transformation is not, and then it can form either a regular normal spiral or it can form barred spiral. So these are the two different kind of galaxies people were aware of at that time. There are bar at the center, and then there's a spiral, and there's a without bar. And so how do these things form? And so he proposed this model. The current understanding, we have much more refined model of that, but Hubble tuning fork stays with more details. So now with that, let's come to the current age. This is essentially showing the growth of galaxy survey across the history, where I think CFA is the first one you can think of, where we had a somewhat largish survey of a few thousand objects to begin with. And then over the last, so something like 1980 to almost to 2030, last 50 years, we have increased the number of objects we observe to 10 to the almost, we'll be touching 10 to the 10 by the end of this decade. So the number of objects have really increased, and you can see the rate of increase essentially per 10 year, it's a power law factor of 2-decade improvement in terms of the number of objects. There was a somewhat slowdown, but we have accelerated. Again, the slowdown was because some of these projects got delayed. And at the same time, there are two kind of surveys here. One is called photometric survey, one is called spectroscopic survey. Anyone have heard of these terms, photometric and spectroscopic survey? We'll talk about more details about this survey, but just to get started, anyone has heard these before? Can I have a, could you say a few words what is the difference, or describe any one of them? Yeah, that's absolutely right. So in photometric survey, we are basically looking at some broad band. What is the total light emitted in certain range of wavelength? And we'll talk about filters and things like that. There are different kind of filters, different kind of photometric survey. In spectroscopic survey, you take the light from whatever source you're observing, and you have a coverage of certain range of wavelength, and you split, you have a very large wavelength resolution. That will, of course, depend on the spectrograph, but then it's fine enough that you'll be able to identify some of the atomic or molecular line transition. For example, one of the favorite for people who are working in a star-forming galaxy is oxygen 2 doublet. So this is something you have heard in the quantum mechanics, right? So when you have this different material, you can have emission and absorption, which are at very specific frequencies, and so you'll be able to identify that. And you can see the spectroscopic survey is lagging behind photometric survey, which is always going to be the case. Another way to think about these two things is that photometric survey is basically somewhat is a 2D survey. So you know position of the object in the sky, and you know their intensity. Okay, you don't know how far they are exactly. The spectroscopic survey gives you a spectra, so you can measure these lines, you can measure the resistance velocity, and you can project that into a distance given a model. Right? So these are more 3D surveys. So they have different kind of information, but that's not entirely true. What happens is that in photometric survey, we have photometric information in different band, different range of wavelength, and that gives you a rough estimate of distance, not exact. This is what we call photo Z, so photometric redshift estimator, but these will have large error. So often people call them as 2.5 dimensional survey, and this is 3-dimensional survey. And because there is much more information per galaxy here, you have fewer number of objects, but that doesn't mean it has lesser information. That is something you have to quantify and look at. In one case, you have 3D information, one case 2.5D, and see what is the information content of that. Yes. So the Z will depend on what survey you're looking at. This is basically how many objects they are going to identify. It will be dominated by low redshift because you're going very faint, and then you'll have fewer number of objects at different redshift. But the redshift will depend on, for example, LSST can go to fairly high redshift because it's a big telescope ground, but Euclid will be dominated to lower redshift. Roman is again a space which you can go to fairly high redshift. It changes survey to survey. If you look at SK, this can go, if you're talking about 21 centimeters, this can go to fairly high redshift and give you a 3D map of hydrogen 21 centimeter transition up to redshift. Even 6, 7, 8, you'll have pretty large density, right? And so we are roughly here. LSST is about to begin, so we don't have this. So this plot is sort of course, not exact. This is a rough estimate. We are roughly here. DESI is already happening, halfway through. We have about 20 or 30 million objects spectroscopically confirmed. And this is a big jump. You can see the previous was about less than a 10 million object. Now we are in the regime where we have 20, 30 million objects. So that's a big jump, and that's going to bring big precision. Right. So there are some standard science case which also I will talk about, which these surveys are doing. But what you want to think about is that whatever your thesis project or project you're working on, how to think about and relate if there is something interesting in terms of the galaxy survey, which is why I'm going to talk about filters and spectra to understand what kind of interactions you might be able to see. Okay, is there any question so far? Okay, so now let's go ahead and see one of the example of how well I said lambda CDM has been very successful. But let's see if we can see that a little bit visually. So this is an image from a very old survey. This is a real observation. Each dot here is the location of a galaxy, right? So there are more higher densities, which means there are many galaxies, low density, which means there are fewer galaxies. This is the redshift axis, same thing in terms of the time. And then what you really see is there's some sort of structure there. It's not all random, especially at low redshift. And so this is what we call large scale structure. And this is a real observation. So this is not any model or any prediction. This is real data. But what you see is that at larger redshift, and this is just redshift 0.2, this becomes more like random distribution. Right? So it's, you don't see any kind of structure like this. Anyone know why? Anyone has seen this or can guess what is happening there? Sorry, who is this? Is the right answer? Yeah, short noise. So this is a short noise, right? So you need to, what is happening is that this is just a flux limited survey. And so now you need to think about if there is an object which is emitting light, what is going to happen to its flux observed from a detector as a function of distance, right? So it will reduce by 1 over r square, right? The surface area of the thing you're looking at. And so for the same telescope, you'll not be able to see most of the object. You'll be limited to very bright object at certain distance. This is something you need to sort of appreciate again and again. And so what is happening is that we are limited to very bright objects here, which almost appears like a short noise here, whereas we can see much deeper here, and so we can see large scale structure in much more detail. If I will increase the size of the telescope and do the same measurement, I will start seeing structure here, which is what we see now with new surveys like DESI. Now, this is from one of the very old surveys, CFA Great Wall. This is from 1980. And what you see is that this very big collection of galaxies tracing this big thing, what is called CFA Great Wall. Now, why is that interesting? The reason it is interesting is that because the way we have set up our universe in terms of the initial condition from the Gaussian random field, it is very hard to form a structure of very big size, right? And if they are gravitationally bound and coherent structure, then explaining that kind of thing is difficult. It's not, so these things are not deviation from lambda CDM, but these things are generally difficult to explain, and you have to carefully take a look whether you're able to explain that or not. So this was known from 1980, and this actually generated quite a lot of excitement since then. But this is in a small volume, and if you go, and again, this is a real observation, and this is again a real observation from Sloan Digital Sky Survey, where you see Sloan Great Wall in the at sort of slightly higher redshift, so this big chunk. And this has all sort of issues. If you have a small volume and you have this kind of measurement, you need to sort of understand how likely to have something like that in a certain kind of universe, and if it is very unlikely, then what kind of things you need to change to do that. So these are what we call basically extreme structure, very big wall, very big filaments and things like that. You might have seen some headlines talking about we have found like extremely huge filaments and clusters in the universe, and these things, these claims needs to be taken carefully, but that's the kind of thing they're talking about. They're detecting these kind of very big structures, and they're talking about, okay, in a lambda CDM universe, if the universe started with Gaussian random field with certain kind of initial power spectrum, and if you evolve it, what is the likelihood to have form one of these things in certain volume? Now, what these panels are showing are actually purely from simulation, which is not matched to the data, but what is matched is that you're roughly seeing the same kind of galaxy, assuming some kind of connection between dark matter and galaxy, so some kind of bias between dark matter and galaxy, and you sort of see similar kind of a structure, similar size of a structure, right? And so this is visually showing you large scale structure from our model and from simulation, and they look very similar. But that's not what our claim that lambda CDM describes these things very well is just on the visual, but since you're trying to develop intuition, it's useful to see this visually. Now ask yourself, okay, visually they look similar, but can I construct something to actually say whether they are similar or not? What kind of thing you want to look at these two images and say, okay, what do you want to compare to say whether they are similar or not? Some statistics maybe, yes. Right, so you can compare 1-point function, you can compare, okay, look at certain size of the universe and look at the density and look at the distribution of density, so that's 1-point function. You can compare 2-point function, so you can say, okay, if I look at pair of point and find out, okay, how do these densities are correlated as a function of distance, is that correlation same in these two things? And so this is what CMB power spectrum was showing in the 2D aspect. And so you can compare that 2-point function. If it is Gaussian random field, then the 3-point function is sort of in the linear regime, so where everything can be evolved linearly, is trivial, but you can also compare 3-point function. You can take 3 different points at random as a function of, now you need to define angles and the distances between these 3 points. And you can do this exercise as a function of those angles and distances and see how the 3 points are correlated and then compare again, right? So these are sort of kind of statistics which you can calculate. Because this is simulation, you can calculate it in similar fashion, but why is it useful? The reason it's very appealing and interesting is that if you look at our sort of theoretical framework, lambda CDM picture, the way we propose initial condition of the universe is in terms of power spectrum. Right? So we are talking about 2-point function. We are saying what is unique in terms of the initial condition of the universe, there is a power spectrum, not the realization, but the power spectrum is something unique. And we know how that power spectrum evolves. So we can actually predict without doing even simulation in certain regime of these variations, we can calculate these things from first principle. That's why also this is appealing, right? So this is what we typically do in galaxy survey. We look at this kind of quantities. So this is one kind of exercise. We also do other kind of things. And we calculate different kind of statistics. Typically 2-point function is the most popular one we often do. And then compare that with whatever your prediction is from theory and see whether you get a match. And then you need to, when you compare something, you also need to think about the errors in that 2-point function. All right. So now that you know that status of cosmology, we have a common picture of the universe, we have some understanding of, okay, we need to calculate certain kind of statistics. In the spirit of motivating a little bit more, what do galaxy survey do? So let me just show some results directly, and then we'll come back to sort of how to go about getting those results. So what this plot is showing is omega matter and curvature, okay? And the gray contours are from CMB, the red one is from CMB plus supernova, and blue one is CMB plus supernova from BU. Both of these things are from galaxy survey, supernova and BU, certain kind of quantities we are measuring. And so if you just look at CMB, we have very broad limits, very broad regions where these things are spread. You add supernova, it's constrained, and then if you add BO, it's even much more constraining. So you can say that the curvature is consistent with 0 at better than 10 to the minus 3 in omega k because of these kind of experiments. So, but how many of you have seen this kind of contour plots before? Not particularly for these axes, the axis could be anything. But how many of you have seen this kind of contour plot before? Okay, so quite a few of them. Do you know what these regions means? What the dark gray and the light gray region is? What is 1 sigma and 2 sigma? What does that really mean? Confidence limits, right? So what is the probability that the true universe is within the gray region? Anyone remember? 68%? Everyone 68%? No one something else? It's not 68%. And what is the probability that it's within the light shaded region? 95%? No, so it's not 68 and 95%. And so this is something actually I wanted to do a little bit more carefully. If you would like to sort of do this kind of calculation, I guess most of you are familiar with Gaussian distribution, right? And so how to sort of represent errors in Gaussian distribution. You talk about a mean and a sigma. So you can have Gaussian distribution is something mu and sigma. Right. So this is 1D version of the distribution. What we are plotting is the 2D. So if you do this and essentially calculate 1 sigma limit, what is 1 sigma limit formally? Right. So this limit, this is the 1 sigma, and this is going to be 68%. Right. So that's the number you are quoting in the 1D Gaussian distribution. In the, if you calculate the 2 sigma limit, all of you have seen this kind of calculation before? This is 0.95, right? So 95%. If I so let's say this is mu, so this is minus sigma, this plus sigma. The area under this curve between these 2 points is 68%. If it's normalized, then it's going to be 0.68. And then if you have minus 2 sigma to plus 2 sigma, then this is 95%. But this is only true for 1-dimensional distribution. If you go to 2-dimensional distribution, the things will be different, right? And so 68% and 95% is not the definition of 1 sigma and 2 sigma. 68%, 90%, 95% just comes out to about to be 1 sigma and 2 sigma. Oops, I think I did something. Okay. Right. So in two sigma regime, right? So when you're talking about 2-dimensional probability, then this is going to look differently. And so how do you calculate this 1 sigma and 2 sigma? The one easy way is that you can say, okay, let's work with the unit Gaussian. So set mean to 0 and sigma to 1. We can set if you define unit Gaussian, then that will be all right. And so if I want to now calculate 1 sigma, it will be minus 1 to 1. Or you can say that minus b to b for general and right, so you can use the Gaussian integral identity, which if I remember correctly is something like right. So if you have a minus b to b integral of this form, this is the identity, and if you use it, what you will find is that this will be square root of 2 pi. Here basically A is equals to half and B is equals to 1 for 1 sigma. So this will be 2 pi so this will be error function 1 over square root of 2. Right, so anyone know what is the error function 1 over square root of 2? I think you can check, but I'm just guessing this will be 68%, 0.68. Okay, and you can similarly do for 2 sigma. This will be error function. No, this cancels out. So this will be error function square root of 2, which is 0.95. So 68 and 95% is not the definition of the 1 and 2 sigma. It's comes out to about, if you calculate what is the area, then that's what it comes out to about in 1 dimension. Now you can do this exercise in 2 dimensional, and what you'll find is that these numbers are different, and these numbers are something like, so this will be, maybe I can give this as an exercise rather than doing it. So 1 sigma limit for a 2D Gaussian is going to be something like 0.39 if I remember correctly, and 2 sigma is 0.87 maybe, something like this. So much smaller limit, much smaller percentage. So the area under those contours is much smaller than the 68 and 95%, the 2 number. So let's do this as exercise, and if you are stuck, then we can do this in tutorial. So during the tutorial, we can work this out. So why is that important? It's important because you need to, when we look at these kind of plots, it's often about intuition, right? So we build some intuition and make some statement. And so when you're looking at 2D contour, you have to remember that this is not 68%. This is much smaller probability for things to be within this. It's 39%, and this is 87%. So there's a much larger probability for that true observation is outside these 2 sigma contour compared to 1D case. So don't take the 1D and 2D 1 sigma to sigma limit equally likely. They are not equally likely. Right, and so I don't know, have you seen this kind of calculation before? You must have plotted, you must have created a plot where you have shown the posterior distribution of some 2 parameters, right? Somewhere, if you're working in cosmology, I guess it's common, independent of what kind of cosmology you're working on. Some parameters you must have done this exercise. How many of you have plotted any sort of 2D contour? Right. So maybe you have used some packages, but it's important to realize that what these packages are doing at the end, and that's the kind of thing sort of will be very important when you're working with any galaxy survey. You often makes plots like this. So yeah, so the point here is that if you use galaxy survey, you can actually constrain things much precisely. If you just stick with the first thing, which is CMB, you don't really know you don't really have you have a limit on curvature of the order 10 to the -1. If you combine that information with galaxy survey, you already get 10 to the -3. For future galaxy survey, the expected forecast is that this limit will be 10 to the -4. So you should be doing better than 10 to the -4. So it's really, really important if you are interested in, for example, nailing down the geometry of the universe. That's the best way to do it. How many of you are working on anything related to dark energy, equation of state, or dark energy model? Anything to do with dark energy? Just one person? 1, 2, 3, 4. Yeah, so this number is already larger than the number of people who raised hand that they are working with galaxy survey. So if you're working with dark energy, then you must be using some understanding of galaxy survey, if not data directly. So when I say galaxy survey, it doesn't really necessarily mean that data directly, but some form of it. So this is a constraint on dark energy, crystal state, and omega matter. And what you see again with the CMB, you have very broad banana, where the vanilla W of -1 is shown there. If you combine different kind of information, right? So if you combine whether you're combining supernova or BAO, you can constrain this much better. And if you combine all of them, then that's this contour. So you can see the dark energy equation state is much more constrained once you include the information from galaxy survey. So if you're working on dark energy model, it's time to think about galaxy survey and realize that you are going to use some aspect of galaxy survey in there. So another interesting thing I wanted to highlight is neutrino mass, right? So some of neutrino mass is something we can constrain through a cosmological measurement. And so anyone working on any aspect of neutrino mass or neutrinos at all? You, so just one person, so 2%. So neutrinos are again something plays a lot of role in terms of the structure formation, and so something you should be able to constrain or talk about with things like galaxy survey. If you combine information from, if you just look at the CMB, then you see this gray banana, and I hope all of you now know what it means when I show a contour like that, right? So we're talking about what is the probability of certain things to be in certain region at certain confidence. And when you want to measure something, you want to measure everything with high confidence. So this is sum of neutrino mass with omega matter. And when you combine CMB with supernova and BAO, you see that things are much more constrained. So galaxy survey is going to help quite a bit in terms of constraining sum of neutrino mass. In fact, there is a forecast that in next 5 years, if everything goes as per plan, we will be able to detect sum of neutrino mass through measurements in galaxy survey. So this is with LSST and the Z forecast says that we should be able to measure. So the more precise statement is that we should be able to measure sum of neutrino mass with a precision of 0.02 electron volt. So if neutrino, even if you assume normal hierarchy, the sum of neutrino mass, the minimum value is 0.06 electron volt, which will at 0.02 electron volt of 1 sigma, it will be 3 sigma away from 0. So you'll have a detection at least 3 sigma from this kind of survey. Modified gravity, right? So anyone at all working on modified gravity in this room? Okay, about 4 to 5 people. So if you're working in modified gravity, again, one of the best way to constrain deviations from GR or be sensitive to what we call growth is through galaxy survey. So if you can measure how the structure which was formed initially, once you set it up, how the structure is growing, and the growth is at certain scale is determined by what is the gravitational interaction of these things, then you should be able to constrain strength of growth. And so this is one such plot where we are really talking about how is the mass interact with each other gravitationally, and how does the photon interact with mass. And so those are the two things. So redshift space distortion, this is the mass interaction constraint that gives you. If you look at the weak lensing and CMB lensing, this is how the photon is interacting with the matter. And if you combine all of that, and all of these measurements are coming through galaxy survey, you constrain these two interaction terms. So it is set up in such a way 0, 0 is going back to GR. If you detect any deviation from 0, 0, then that's deviation from GR. Yes. Mm-hmm. So if the constraints are seen, does that mean that the low ends do not have, or large scales do not have an impact on these parameters? So let me understand the question a little bit better. You're talking about ACT, which is a ground-based experiment, which has much higher resolution, and so you're able to probe more small-scale fluctuation in the CMB. Whereas Planck have lower resolution, so it misses out these small scale features. So as if you're taking a fluctuation and you're filtering all the small scales at a certain scale. And so the question is whether the ACT measurement is consistent with Planck measurement is the first part. And what's going to happen is that especially in this kind of space, the constraining power of these two experiments will determine a lot of things beyond the resolution. So for example, what is the area of the sky you have covered? Okay, what is the sort of noise in your measurement, in the temperature measurement? And one thing where, as well as the range of scale accessible to it. So what Planck does very well is that it pretty much have all sky. Of course, you have to remove our own galaxy. So it has a significant part of the sky. And so you have smaller error, although you do not have access to the large L mode, so smaller scale. Whereas ACT is a limited patch of the sky. So it doesn't have large scale information that well. And so if you want to constrain these kind of things, what's going to happen is that if you look at individually ACT versus Planck, the errors are going to be very different. And so if error is going to be very different, if one of them has large error, it will always come out to be, unless there is a discrepancy at that large error level, to be consistent. So right now, the ACT and Planck lensing, if you compare them, they are consistent with each other. And hence their modified gravity constraint is going to be consistent. Individually, if you look at them, then the errors are going to be different. And so what this is looking at is, in fact, what this is looking at is only the lensing part of the CMB. So you know the CMB, you can look at the fluctuation and correlation in the temperature itself, but you can also look at the lensing, how these fluctuations you're looking at is being lensed with all the intermediate objects or matter distribution. And so this is only looking at the lensing part of it, and that is consistent between the two right now. The next part of the question I didn't quite follow. You made something about insensitive to parameter if they are consistent. Yeah, so certain modified gravity model, in fact, changes things as a function of length scale, and at certain length scale, they will all converge to the same thing. There are different kind of screening mechanisms to make sure that at solar system scale, you always are consistent with GR, and so that can make a different kind of model to be more sensitive with ACT or Planck data because they have access to different scale. These are more generic model where you don't have such a strong scale dependent, and so there everything is consistent. But you can, in principle, create a model where you might be more sensitive to ACT with ACT data, but not with Planck if they are focusing on the range of scale which Planck do not have access to, but ACT has access to. All right, so now let's look at anyone working on any aspect of dark matter physics. 1, 2, 3, 4. Right. So if you're working on dark matter physics, anything to do with dark matter physics, there are many ways to probe dark matter. And so this is a list of it. It might be missing some of your favorite thing, but I tried to make it exhaustive just so that you know what are the different ways to probe dark matter. We start with gravitational lensing. So this is essentially looking at how does the light gets bent in the field of dark matter. So when you have the galaxies or dark matter halos, and so experiments like DES and LSST and Euclid will be probing gravitational lensing, which will give you a stronger constraint on the dark matter beyond what we already have. There are galaxy rotation curve, so you can look at the galaxies and as a function of radius or distance, you can look at what is the rotational velocity of things. This can be done with radio telescopes, or you can also do this using spectrographs. So you can look at the recession velocity, where if things are coming towards you and away from you, you can look at create a map of how these things are evolving. And so these rotation curves will also give you access to certain aspect of dark matter at certain scales. There are galaxy cluster dynamics. So you can look at these big objects which are galaxy clusters. They are very massive halos in the universe. They're full of galaxies, they're full of hot gas, so they are very bright in X-ray. So you can look at various components of it. You can look at the X-ray component, compare that with the velocity dispersion of the galaxies. That will tell you, okay, what is the sort of potential well of the dark matter at that cluster kind of scales. So that's another way to look at. Very close to us, you probably have heard of bullet cluster, which is basically a system we think is of merging galaxy. And so you can look at the light at various wavelengths and look at the stellar versus dark matter component and see what are the kind of interaction when two blob of dark matter merges. And based on whatever interaction you're proposing, you'll see different kind of features. So that's another way to constrain that. There are stellar streams. So these are very interesting part of the galaxy survey. We actually observe lots of stars, although it's called galaxy survey, right? The stars are observed for various reasons. Sometimes it's observed because you want to do certain kind of science. For example, you probe dark matter. Sometimes it's observed because you want to calibrate your system. You want to know how bright or faint a galaxy is, and if you know certain stars, we can use that to calibrate your systems. Sometimes it's observed to understand what the atmosphere is doing in between. So these are called, in radio language, these are called phase calibration. So we often observe lots of stars for various reasons. And so if you look at the stars in Milky Way, sometimes you find these streams of stars. So basically a line of star which is going through the Milky Way. Now imagine a line of star moving in a gravitational potential well of Milky Way. Imagine a symmetric gravitational potential well of some mass, right? So they will have certain dynamics. Now, if you look at these streams, they will be actually very sensitive to the details of certain aspect of gravitational potential well itself. But they will also be sensitive to any kind of objects or dark matter, compact objects, which may pass through this line and interject. So if you propose there are these compact objects exist at certain density, you can calculate how often a stream can get disturbed. And so that's another way to measure certain properties of dark matter or detect these compact objects. Many galaxy survey will have large number of stars, including DESI and LSST, and people are going to look at these stellar streams to probe certain aspect of dark matter or probe compact objects. Now, so these are all in different color because these are all observations coming through galaxy surveys. Yes.
JWST is seeing some banana-shaped galaxies with galaxy clusters. So do we know that what is the dark matter profile for such things, or what kind of dark matter gravitational potentials can make such structures along this lines?
Yeah, so that's an extremely complicated problem because it's not just the dark matter. When you talk about the scale of the galaxy and the shape of the galaxy at that level, right? A lot of galaxy physics, like how did that galaxy come to form? What are the kind of material? Is it really falling in? Is this galaxy still forming? All those needs to be addressed. And so these are called all the galaxy astrophysics related problem. So for JWST galaxy, typically if you're talking about high redshift galaxy, which are in very early universe, redshift 12 or 14, then we think that these are early stages of galaxy formation. And so in principle, it might be possible that, in fact, most of the galaxy is expected to be very irregular at such a high redshift. But from theory point of view, to calculate that, you have to run very hard simulation. It's not something you can do with analytics. We know the basic setup, but you have to do these simulations, and people are trying to do that to explain these different shapes of the galaxy. But we don't know. We don't have the answers yet. Right. So these first 5 are basically everything is through observations of galaxy surveys. But there are other ways to probe aspects of dark matter. One is for example, cosmic microwave background, where you can look at, which is actually what gives you the precise measurement of amount of dark matter, the first precision measurement, if you look at the temperature power spectrum, or the CMB lensing part of it. There are many direct detection experiments. So there are a large number of these direct detection experiments happening I don't know too much about them. I've only read very basic introduction to those things, but you can look at some of the famous ones. For example, something like Super CDMS or CREST, where you're looking at crystals to detect photons, to look at the dark matter interactions. There are xenons and lux, which is again using certain kind of medium to see if we can detect dark matter interaction. There's PICO, COPE, DAMA, Libra, NS. So these are all detailed particle physics experiment, and I'm not an expert, but I wanted to make sure that you know that this exists. And if you are interested in detailed particle physics aspect of dark matter, feel free to go and read about each one of them. There are also indirect detection experiments. So these again comes back to astronomy. So there are gamma ray telescope and neutrino detectors, which can detect if, let's say, dark matter has certain kind of annihilation, particularly if there are certain kind of particle which can annihilate, then they are expected to emit in these kind of wavelength, gamma ray, and they can also emit neutrinos. So those things can be detected through gamma ray and neutrino, and there are groups who are actually looking at. In fact, there was some recent first sky map of neutrino was measured probably 6 months ago, and not that long ago. So those can be used to detect dark matter. There are more specific axion searches where you're looking at particular, you're saying that dark matter is a certain kind of axion, and then you can look at a certain kind of particle physics interaction for them. And then there are also atomic molecular optical traps where you think if dark matter interact with photon in certain way, then you should be able to detect their signature in that. And so there's a large variety of this. Almost 50% of these methods are through galaxy surveys. So if you're working in any kind of dark matter modeling, there's 50% chance that you will be looking at some aspect of galaxy survey to do that. Now let's go on and look at probes of dark energy, right? So now you can see the probe of dark energy. Again, the color coded is same. All this has to do with galaxy survey. This is not by my definition of galaxy survey. So there's 90% chance if you're working in any aspect of dark energy, you're going to look at certain aspect of galaxy survey. So now these are essentially the probes of dark energy, and one of the important thing what you should look at if you are interested in any aspect of dark energy, what are the things it's sensitive to. So the famous one is, of course, supernova, which measures distance redshift relation. It essentially says that as a function of redshift, what will be the distance, and that will be function of dark energy equation of state. Baryon Acoustic Oscillation again does the same thing, and these two are the most famous and most constraining right now. It measures angular diameter distance of BAO peak, and that gives you distance relation, which can then again constrain dark energy equation of state. You can look at weak gravitational lensing, which is essentially probing the growth of structure. So evolution of sigma 8 to extend if you fix everything else. And then that, especially at low redshift, that's very sensitive to equation of state as well. You can look at the number of clusters, just the 1-point function of clusters. So how many clusters you find per unit volume. And if you look at the number of clusters, then that will be to an extent, it's not very sensitive, but it will be sensitive to dark energy equation of state again. You can look at redshift space distortion, which is essentially saying if these galaxies which you're looking at, they are interacting with each other, so they have peculiar velocity. So this peculiar velocity will appear in certain kind of statistics if you are able to measure that. And so if you are able to measure these statistics, what you are basically able to measure is how fast these things are moving, what is the peculiar velocity, and that is sensitive to both modification to gravity as well as dark energy. You can look at AP test, time delay cosmography, and 21 centimeter hydrogen survey. So I don't want to go into details of each one of them, but see, these are the basically various ways we can probe dark energy, and most of it has to do with galaxy survey. So I hope by now you are convinced that most of you are working on galaxy survey. So how many of you are working on anything to do with galaxy survey now? Given you're working on all these different things and galaxy survey has overlap, I hope you'll realize that you're working with a certain aspect of galaxy survey independent of what problem you're working on, whether you're working on dark matter, dark energy, neutrino, or certain aspects of fundamental cosmology like geometry of the universe. You're working on galaxy survey. So now let's go into sort of what do you see in the sky. And so I will briefly show an image, but then we'll talk about this in more detail in the next lecture, right? So if you go and see in the sky, let's say your eye is as big as 4 meters, because this is an image from a 4-meter telescope. If your eye is as big as 4 meters, this is what you are going to see. Okay, so what do you see in this image? And you have to be in a fairly dark location. So you will not see this in the, even if your eye is 4 meters, you will not see this in a city like Bangalore or Mumbai. You have to go to a very dark location like Hanley or Chile to see these kind of things. And so what you see is this is the size of the moon roughly. What you see is that each of the dot is essentially a galaxy, which essentially looks like a dot, right? So you don't really have much information, it's just a point. How can you do any sort of precision science with just dots? So you need to do something more. Just seeing them is not enough. You need to extract more information about that. So for example, you have to figure out, okay, what kind of things these are. And how far these things are. So one of the things, let's say if you want to make a map of the galaxy in the universe, one of the most important things is you also want, apart from the position in the sky, so you can measure their angles, 2 angles to determine what is their position in the sky very precisely. You also need to figure out how far these objects are. And that's what gives you 3D images. And so you can do that either with a photometry or you can do with a spectroscopy. But let's say galaxies are of many kind and they are basically continuum. But if you imagine that there are roughly 3 different broad categories. One is active black holes. So these are galaxies which has supermassive black holes at their center and then they're accreting. These are galaxies which have young star formation, so they look very bluish if you were to see that with naked eye, if it's possible to see that. And then there are more sort of elliptical old galaxies where not much star formation going on. If you're, let's say, there is 3 kind of galaxy, what you could do is you could go and observe a spectra of each of these galaxies, and then you'll be able to look at these features and talk about how that relates. But you can take light from each of these galaxies and split it as a function of wavelength, and so that's what spectra is going to look like, intensity. And so if you were to do that, then you'll be able to identify each of these galaxies, their nature, as well as you'll be able to identify what their distances are. And so now you know the 3-dimensional map of this. Of course, I'm still plotting in 2D because I'm plotting very small slice of that 3-dimensional map. So the depth is very limited in this plot. Now what you can say, okay, I'm finding galaxies to have some sort of a structure, and if I invoke that, since everything is forming in sort of the same potential well to begin with, let's say there's a dark matter collapses and forms potential well, that's what the ideal place to form galaxies, right? So for gas to condense and compress and form stars and then form a collection of that and galaxies, if I look at dark matter as some sort of density distribution in the universe, wherever there is a high density, I expect there to be more of these gas to collapse, more galaxies to form. And so the galaxies and dark matter distribution itself are correlated, right? But they are not exactly the same thing. And so this is what we call it, bias tracer of the dark matter. Galaxies are bias tracer of dark matter. This statement was made by one of you earlier on. So when I'm probing the large scale structure fluctuations in terms of the density, I can actually estimate roughly what is the dark matter density in different patches of the sky. And this is what it is. It assumes some sort of bias. And then this bias, which I'm talking about itself, is going to be a function of what kind of galaxy you're looking at. So it will be different for different kind of galaxies. So if you're able to do that, then you can essentially make map of dark matter of the universe. And now once you have a map of dark matter of the universe, you can calculate all different endpoint statistics and then compare that with your theory. So that's the large scale structure part of it. Okay. So this will sort of gives you this kind of thing. So when you go to the night sky, you basically see stuff like this, but you have to extract details to make information like that, and that's where we are going to then learn or ask any of these deeper questions I told you, either about dark matter or dark energy or anything about cosmology, to figure out, okay, how to constrain that. What I really want during this set of lecture is for you to give some flavor of how to think about your problem, whatever that might be. I'll give you some example and put it in the context of galaxy survey, and maybe how to go about and try to see what will be the constraint I can obtain if I were to do galaxy survey. What kind of usual statistics people look at. All of this requires a lot of understanding of structure formation itself, but that's not what this lecture series is about. So I'm not going to cover details of the structure formation, but I hope I'll give you intuitive feeling about that, and we either already know or there is enough material available with which you can go and read about structure formation. Yes. Mm-hmm. Mm-hmm. Yes, yeah. So not the higher resolution. Let's say if you have a bigger telescope, what's going to happen is that you'll be able to see fainter galaxy. There's a lot more galaxy than you see in this image. And it's all limited by how faint you can see. Let's say if you have a bigger telescope, which we are going to have, LSST, for example. This is a 4-meter telescope, LSST is a bigger telescope. You're going to see a lot more fainter galaxies. And so if you are able to see a lot more fainter galaxy, this distribution is going to change. But this distribution is going to change at certain level. It doesn't mean this whole density will disappear. What you're going to find is that there are many more galaxies here, right? But like these things are not connected. For example, this patch is not connected and it's very sparse and noisy. What we're going to find is that a smooth transition. So basically you will approach what simulation shows in principle. When you have more and more deeper and deeper sample. If you have deep enough samples, in the galaxy bias approaches 1, which means you're basically probing dark matter. If you're measuring all the faint galaxies, you're approaching galaxy bias of -1, you're making dark matter, you'll have much better picture of this thing. And so at a certain scale, this assumption of linear bias, which I'm applying here, breaks down. And so the bias becomes a function of scale. And at those scales, whatever you're going to infer is going to be wrong. And so you need to start modeling this nonlinear bias if you go beyond certain scale. At large scale, everything will look more or less the same. If you take this deeper map and sort of smooth it out, you'll come back to this picture. So that's the idea. So this is a smooth version of the true density map of the universe. Okay, so I think this is where we are sort of 2 minutes left. So I'll sort of, I'd like to stop here. And as a summary, I hope you have sort of a broader picture of what it entails in terms of galaxy. When you say galaxy survey, what are the kind of things it can do, what it already does, the ability and power of galaxy survey, the kind of thing, like at least some rough kind of thing you have to worry about, some kind of statistics. You can now look at 2D contour and sort of understand what is the probability within the area and what are people plotting. And so in the next part, what I'm going to do is that we'll sort of start talking about essentially now that you have this rough idea and this is what you can do, what is it you want to observe? Like, what do you want to observe? What kind of detector you want to look at? And what kind of information that will contain, what kind of physics that will constrain. So we'll slowly make progress in this direction in the next few lectures. Thank you. Yeah, sorry, any questions? I forgot, of course. Sorry, where was this from? Yeah. So what is galaxy bias? That's a great question. Formally, the way we define galaxy bias is, so there's a famous paper by B.B. Case, which essentially says that, let's say the distribution of matter in the universe is represented by Gaussian random field, which means there are fluctuations of different kind, right? So imagine this in 3 dimension, but I'm looking at only 1 dimension. Now, if this is dark matter, the gas and baryons and everything will follow roughly the same thing. And wherever there's a higher density, you expect higher number of things to collapse and form, and then they will disintegrate. So let's say if I'm saying that I can only look at, so galaxy number density will follow somewhat this kind of structure, but let's say I can only look at galaxies brighter than certain limit, which means if they are related with each other, I can only look at peaks above certain height, right? So if I draw a threshold here, I can only see this peak. I do not have resolution to see the lower peak. But if, let's say, if you can go deeper, you can see these peaks, right? And if you can go all the way deeper, you can see everything. Now, if this is represented by Gaussian random field, and if you denote by delta, delta is the over density of this thing. So formally it's defined as so this is the matter density. This is a full dark matter distribution. I'm writing in terms of over density. If I can only see this peak and define the density in terms of this peak, these are all quantity in terms of peak. How are these two things related? So you can show explicitly in a Gaussian random field scenario. And the Gaussian random field is important because that's what gives you the size of a scale it is applicable. You can show that this delta p, which you are going to determine, is related in this fashion. Okay, and so the term here, so what this statement is that this peak distribution and the matter distribution, the whole Gaussian random field, is related by a scalar, and this scalar is scale independent. This is what galaxy bias is, or B. And then you can measure this in real data through various statistics. For example, you can look at, no, sorry, this is not B square. I'm too much into the 2-point mindset. So this is just B. So you can measure this because I talked about correlators, right? So you can look at this quantity. This is what the 2-point function is going to look like. We have seen this in terms of the CMB. We have discussed that. You can also calculate this delta P, which is what we do for the galaxy. And if you relate them, where this thing you can predict for any cosmology you want. You can predict it through perturbation theory. This thing something you can measure, and so with for a given cosmological parameter, once you have this measurement, you can measure galaxy bias. Yes. This B, so this B will not depend on the scale in the linear regime. So when you actually, when this is represented by essentially Gaussian random field, but when galaxies form, the size scales around the scale of galaxy or the dark matter halo, things are not linear anymore. And so that's where the Gaussian random field assumption I said is very important. At linear scale, this is strictly true. At nonlinear scale, if you want to write this, then this will be function of scale, B of R or B of K. So, so typically how it will look like is that if you have radius and bias B of R, at some scale, at large enough scale, this will be some constant value. At small scales, this will have nonlinear contribution. So if you know this, and this is an sort of a difficult question, if you know where this point is, you can model this with just linear thing, and you can do your cosmology, and you can say, okay, I'll forget about this because this is hard. Or you can try to model this as well. So with approaches like effective field theory, you can try to model that. Or you can, since you can't determine this exactly, you can be more conservative and say, okay, I know for sure it will be constant beyond this scale, I will just use this. So the first order galaxy information, whatever forecast you saw, basically uses approach like that. Now we are tending more towards trying to model this with effective field theory in the modern galaxy survey, and that's the hard part.
Just a request that if you ask any question, please try to use the microphone, because we have a number of participants who are attending online. And so they can also listen what questions are being asked and what this discussion is going on. So let us thank Shadab for this wonderful lecture.